This is the start of section 11.3, Systems of Nonlinear Equations, two variables. What we're going to do is we're going to return to systems of just two equations and two variables, x and y. So no z in this section, just x and y. But now what's different is one or both of the equations will be nonlinear. The graphs of nonlinear equations are usually curves in the xy plane. Parabolas, circles, ellipses, hyperbolas, or even other curves. The solutions to the systems will be coordinates of points of intersection of the graphs of the equations. Since the graphs may intersect at more than one point, we will often obtain more than one solution. Here's the first example we're going to look at. Solve the system x squared plus y squared equals 9 and x minus y equals 3. Now, we are very familiar with both of these equations. X squared plus y squared equals 9 is the equation of a circle. And x minus y equals 3 is the equation of a line. So one of these equations is linear, one is nonlinear. So even before we start doing any of the algebra here, we have an idea in our minds that we have this circle graph, and then we have this line, and we're looking to see where those might intersect. And it's possible that there could be more than one point of intersection. So let's go ahead and get started on this exercise. I'm going to start on a separate sheet here. And so our main strategy in solving these nonlinear systems is going to be based on the substitution method. And so here's how we're going to work. Let me just want to say substitution here is going to be the key for most of these. And so I'm also going to label these equations. Let's label them number 1, number 2, so we have a way of referring to them. So what I'm going to do is I'm going to isolate one of the variables in one of the equations. And there can be more than one way to do this. There can be many ways to do it. Here I choose, I'm going to make a choice to isolate, I'm going to choose to isolate x in equation number 2. So let me recopy equation 2, x minus y equals 3. And by isolating x, it's pretty easy to do that. In this one, I'm just going to add y to both sides. So x is equal to 3 plus y. And then I'm going to substitute into the other equation. So in this case, the other equation is equation 1. And let me recopy equation 1, x squared plus y squared equals 9. Now the substitution I'm going to make is determined by the isolation that I did with equation 2. So I'm saying x is equal to 3 plus y in this system. So I can replace the x in equation 1 with 3 plus y. And since I had x squared, I have to realize that I need to take the quantity 3 plus y and square it. Plus y squared equals 9. And now I have an equation in one variable that I can solve for y. So the idea of substitution is you obtain an equation in one variable that you can solve. Now, I think we all know that 3 plus y squared is 3 plus y times 3 plus y, so I have to multiply out that expression in parentheses. 3 times 3 is 9, plus 3y is plus 6y, plus y squared, plus then I have the y squared that's already there, equals 9. So here I have 2y squared plus 6y plus 9 equals 9. And I can subtract 9 from both sides of the equation here. And I'm going to get 2y squared plus 6y equals 0. That's a quadratic equation, and it's of a fairly simple form. I can factor it. I can factor just by removing common factors because I have only a y squared and a y term. So I can factor out 2y times y plus 3 in parentheses equals 0. And so now I can split this up by the 0 property into 2y equals 0, or y plus 3 equals 0. 2y equals 0, I have to divide both sides by 2 to get the solution y equals 0. Y plus 3 equals 0, I have to subtract 3 from both sides to get the solution y equals negative 3. So I have two solutions for y, and because I'm solving a system, I still have to find the corresponding x values. For each one of these, so I have to take y equals 0, and I'm going to plug that into an earlier equation that has x and y. The easiest to use is where I have x isolated. X equals 3 plus y. So if y is 0, x is equal to 3 plus 0, or x is equal to 3. That means 3, 0 is one of my solutions to this system. From the other y value, I'm going to also plug into x equals 3 plus y. And so x is equal to 3 plus a negative 3. X is equal to 0. So I have a kind of looks similar, but it's different here. X coordinate is 0. Y coordinate is negative 3. I get 0, negative 3. So I'm done with my solution. There are two solutions to this system, 3, 0, and 0, negative 3. And we just solved a nonlinear system where we had two solutions to the system. And what I want to do is, just before we quit this video, I'd like to just take a look at the graph of those two equations, the graphs. And they're fairly easy to graph, so we're going to be able to do this pretty quickly, because x squared plus y squared equals 9, we've already observed is a circle. And I know the intercepts of that circle are going to be at 3, 0, negative 3, 0, 0, 3, 0, negative 3. So my circle graph is going to look kind of like so. There we go. And now to graph, So that's the graph of x squared plus y squared equals 9. To graph x minus y equals 3, I guess it's easiest for me if I just observe that I can write that as x minus 3 equals y, or y equals x minus 3. So that's a straight line with y-intercept at -3 and slope equal to 1, the x coefficient. So here's my y-intercept at 0, -3, and I can get more points on that line by just going up 1 over 1, up 1 over 1, up 1 over 1. Let me get my ruler out here. And let's draw that line. Okay. So here's our graph of x minus y equals 3. Here's our graph of x squared plus y squared equals 9. And the circle and the line cross at 2 points. They're both intercept points. Here's one of our points is 0, -3. Here's the other, 3, 0. And those were the 2 points that we got as a solution for our system. So stop this one here. We're going to do some more exercises. So basically we're just going to do several more of these nonlinear system problems.